This lesson is on the first fundamental theorem of calculus. At the end of this lesson, you will have an actual algebraic way to evaluate a definite integral by using our antiderivatives. We abbreviate the first fundamental theorem of calculus as FTC1, and it states if a function f is continuous on the closed interval from a to b, and capital F is an antiderivative of the function f on the closed interval from a to b, then the integral from a to b of f of x dx is equal to capital F of b minus capital F of a. Now think about what that is, and think about how we've been evaluating integrals so far. We're taking an antiderivative. So this is saying if you do an integral of a function f, capital F is simply denoting that antiderivative you find. What the first fundamental theorem of calculus tells us is that the definite integral is the value of that antiderivative at the upper limit of integration minus the value at the lower limit of integration. If we go back to the statement of the theorem, notice how we're substituting the upper limit of integration first, minus, and now we substitute in the lower limit of integration into that antiderivative. Since capital F is an antiderivative of function f, when you take the derivative of the antiderivative, and notice how we denote that, capital F prime, the derivative of an antiderivative, you get the original function, lowercase f of x, back again. So what the first fundamental theorem of calculus is confirming for us is what we saw some of in the first lesson, that differentiation and integration are inverse operations of each other. I mentioned at the start that we will now have an algebraic means of evaluating a definite integral, and we're going to use the evaluation of the integral 1 to 3 of x squared dx as our example. The first thing you'll do is find your antiderivative, in this case the antiderivative of the integrand x squared, which yields 1/3 x cubed, and we're going to evaluate that from 1 to 3. Notice the notation that we use to indicate that we have here an antiderivative, and we're going to evaluate it from 1 to 3. The square brackets you see here are pretty standard in terms of how we write this out by hand. Once you have your antiderivative, we're going to evaluate that antiderivative at the upper limit of integration minus value at the lower limit of integration. If we substitute in 3 first, we have 27 over 3 minus, it's always a minus there. Now we substitute in 1, and we have a third. 27 thirds minus 1/3 is 26 thirds. If you prefer a decimal answer, it's 8.6 repeating. The great thing about these is you can check them all on your graphing calculator. So let's go ahead and take a look at that, and we'll look at both ways that you can use your calculator to evaluate these and check your answers. You have a couple options. You can put the function, the integrand, under y equals if you'd like. And I'm going to do that on this only because I'm going to do it graphically the second time I show you how to do this. For my purposes, it might be easier to have it here under y1. Once I have my equation in y1, I'm going to go back to my quit screen. You want to pull up Math 9. Notice Math 9 is function integral. It's comparable to what you had with nderive, except now you're doing integrals. And assuming you have the updated operating system, yours should look like mine here, and we're simply going to type this in just like we had it given to us. So we're doing the integral from 1 to 3. Our integrand here, I can simply either type in x squared right here, or I could pull up y1. Either one is fine. And then we are taking the integral with respect to x. Hit enter, and there's that answer we got. If you go to the graph, remember I had put my integrand under y equals. I'm going to go ahead and graph that. Now I'm going to do this graphically. The other way in which you can evaluate a definite integral on your calculator from the graph, if you do second trace, so number 7, notice it's asking you first for the lower limit, which would be 1. Hit enter. Now it's going to ask you for the upper limit. And notice how it put a vertical line here? to mark where that lower limit is going to be. The upper limit was 3, and hit enter on that. Notice it shades it in, and there's your answer, the 8.6 repeating. What you need to remember with definite integrals is that different interpretation, different from what we saw at the beginning of the unit, as really being now the area under a curve between two boundary points. Now, perhaps you're asking yourself as we went through that example, well, what happened to the plus c we used to have with our antiderivatives? Remember, antiderivatives were also known as indefinite integrals. They're integrals with no boundaries, and that's really why we needed the plus c, the constant of integration. With definite integrals, you do not need plus c any longer. And I'm going to walk you through a little algebraic mini proof as to why. Suppose we consider the integral from a to b of f of x dx. Well, I know my first step is I need to take the antiderivative, and I'm going to call upon the actual statement of the first fundamental theorem of calculus for this. Remember that we called that antiderivative of lowercase function f, we called that capital F. So when I take my antiderivative, I have capital F of x, and I'm going to include my plus c for now, like I was trained in the first lesson to do so. And we're going to evaluate this from a to b. Notice the square bracket notation I showed you on the earlier slide. The first fundamental theorem of calculus instructs us that we first evaluate this antiderivative by substituting in the upper limit of integration. So we would have capital F of b plus c, then it's minus, and now we substitute in the lower limit of integration, a. If we were to start simplifying this expression, we could now distribute the negative over that second quantity. We then have capital F of b plus c minus capital F of a minus c. Notice the c's cancel out, and all that remains is capital F of b minus capital F of a. And that is why when you do definite integrals, you do not need the plus c's because they always will cancel out. So for the sake of efficiency, we simply eliminate them as we do a definite integral problem.